Hello, everyone. Come on in. Hope you all had a great weekend. Hope you're ready to learn some more physics. Or as Sheldon was so upset with, a little physics. Anybody have any questions while we're waiting for everybody to come in?
I have a question.
What's up, Nick?
The practice test is due this Wednesday, but test 3 isn't due till next week. Is that correct, or is it supposed to be due the same day?
The practice test is technically they're sort of never due. You're not required to do them, but I usually try to make them disappear about the same time as the test. So that's the oversight on my behalf. I'll make sure I sort of align them. If I don't remember, by all means text me, but I'll do my best to remember. I usually, like I said, there's no advantage to you doing them after the test. And in fact, students like sometimes go back and do that when they realize they did horribly on the final exam, and I'm not letting that happen anymore. So it'll disappear shortly after the test.
Okay, sounds good. Just wanted to clarify on it.
No problem. And test 2, I think, is due really soon, like March 1st, or is that test 3?
It's test 3.
Okay, cool. Make sure you guys don't miss it. I did get an email from somebody that had some technical difficulties, didn't take it, so I got to open it back, test 2 up for someone else. If it's one of the people in here, I did receive your email. I just haven't replied yet. Lots going on at the Younger house. Anybody else have any questions? Were y'all able to get a chance to solve some of those circuit problems from chapter 26?
Yeah, they were a monstrous pain in the ass. Some of them, at least.
Yeah, you got to do a couple before you get the hang of it, and by then you're like already know how bad it sucks to screw up a little bit in algebra and arithmetic. And then if you don't see a quick trick, you feel like you can't do anything. Remember, you can always set them up as some number times I1 plus some number times I2 plus some number times I3 equals just a pure number or something like that. And then you could use the Gauss-Jordan method if you wanted to. So that's always a possibility. Obviously, that's kind of ugly and you don't want to do that unless you have to. But if you're ever in a pinch, that's one way you could do it. Obviously, you'd have a lot of zeros in it, and that you could reorder the rows then, and that'd make life a lot easier. Because normally when we do the Kirchhoff loop rules, you don't have all the currents in one equation, so you have a lot of zero coefficients for, say current 2 that's not in equation 1, and then you get them so that they're already stacked where the zeros are down below the diagonal. So that sometimes can help. Or you can use Kramer's rule where you have to do the determinant and all that stuff. Anybody else have anything? Nothing exciting? Well, we'll knock out chapter 27 today. It's a pretty straightforward chapter. I'll start off talking about basically magnetism, which we know has been known for thousands of years. In fact, it was first given the name magnetism because it was based on stones that were found in a place they call it Asia Minor, which normally when people say Asia Minor, they generally just mean what's now Turkey. But I think there's a part of Asia Minor that some people would define as around the edge there over on Greece. So it could have been anywhere in there, but the area of Magnesia, where there's actually a ancient stadium, was actually in Anatolia or Turkey. So it's that area. But they literally found stones that would stick together through some magical force. So they named that magnetism after Magnesia, where they came from. And that's what we're going to learn about today, is basically what is magnetism. Not so much what causes it, but the next chapter is going to be more about that. But definitely more in terms of, okay, well, what forces can it apply to things like charged particles or moving charged particles or current carrying wires, stuff like that. So it turns out that there exist magnets. We'll learn more about the microscopic details about how it works, but basically there's certain materials that will align. In other words, they have this polar property where they have sort of a axis of symmetry or axis of asymmetry or something weird like that tends to align with other ones just like it. And then there's these whole neighborhoods of atoms or molecules within the substance that all align the same way. And in fact, if you get them up hot enough, they can be released freely enough where that factor will dominate it, and you might actually get an even bigger neighborhood or region with all those things aligning. And when you do, then you have a full-blown magnet. And it turns out that with a magnet, there's a North Pole and a South Pole. The easiest way to actually make one, and this is what I used to do at a hands-on science museum that I was part of opening up in Elizabeth City, North Carolina, called Port Discover. Basically, you could take a sewing needle, which is generally made of steel, iron, and you take it and you just rub a magnet on it. So you take a magnet you already have, in other words, and you rub a magnet on it. You don't necessarily have to do that. You could actually make one from scratch, and that would just require you to, say, wrap a wire around that iron needle, say, and then run a current through it, appreciable current, and that's going to make all the stuff align along that, all the atoms with those little polar parts align along the axis of that needle. Either way, whether you rub the needle, or, and I say rub, you actually don't even have to touch it. You just have to bring it near it and keep on repeating the same motion for a little bit. Or if you make an electromagnet out of it by wrapping wires around it, once you pull that needle out of that situation, you can then center it up on top of a little cork, C-O-R-K, you know, like you cork off a wine bottle with, and touch a little dab of hot glue on it, or Elmer's glue, and let it dry. And then you can take that little cork and stick it in a body of water. And if you really got it centered up pretty well and you've got it magnetized pretty well, then automatically one end of the magnet will point towards sort of our geographic north. Okay. In other words, fairly close to our North Pole. It turns out the actual magnetic North Pole is actually a South Pole, and it's not really at the North Pole. It's more like in this big body of water in northern Canada. And it moves rather fast. It moves on the order of a couple kilometers a year, and it's constantly moving. Not only that, in the last 330 million years, it's flipped directions over 400 times. So roughly every 900,000 years or so, it just completely changes from South Pole being at the top and the North Pole being at the bottom, vice versa. And we don't know. I think they believe that's a rather quick change, but we don't really know for sure. But anyways, so that's a way you could make a magnet. And in so doing, you've now made a compass, because when you put it in the water, it becomes a compass. And since we call that end of the magnet that points towards the North Pole of the magnet, we then have to realize that the North Pole of the Earth is technically a south magnetic pole. So keep that in mind. You can sort of think of the Earth like this, and it has a bar magnet, say, leaning that way towards northeastern Canada. And then, of course, 180 degrees around the other side is the south pole, the south magnetic pole of the Earth. Well, I say it's the side that we call the South Pole, but it's technically a north magnetic pole. And you can sort of picture the Earth as if that bar magnet's inside of it, and that gives us a good idea of what the magnetic field lines look like. I'm going a little bit on the assumption that you guys have seen from grade school or whatever. When people put down iron filings over top of a magnet, you can sort of see how the magnetic field lines go. But basically, let's say if this was a bar magnet, okay, if this was a bar magnet and this was the North Pole and this is the South Pole, okay, what basically happens is the magnetic field lines actually point out of the north. I often joke that it's like old people. They leave the north and enter the south, right? Because most people don't. Let's move to Massachusetts for for our old age. No, they don't want that, 12 inches of snow in 3 minutes sort of thing. So they want the nice warm weather in Florida. So they, obviously move from the north to the south. The same thing happens with magnetic field lines. They emanate from the north and then they enter the south, but they're not like field lines for charged particles where they start on a positive particle and end on a negative particle. These actually go in a complete loop. So this one, just off a little bit angle from straight up, would actually go this way, make a loop back around, come back inside, and go right along the inside of the bar magnet. And if you went a little bit to this side of it, it would be a little tighter circle and then go around through it. And if you went a little bit towards the middle, it'd be a bigger circle. And just like in the electric field cases, when lines are really close together per unit area, that means they're very strong. So obviously the strongest magnetism is right along the shaft of the magnet itself, and then near the poles. because everything else is spreading out and has these lobes like this. Same thing by symmetry, you can guess that this side would look about the same. But remember, the field lines exit the North Pole and enter the South Pole. And here's a neat thing. If you took this magnet and you cut it in half, you might think, oh, cool, now I've got a North Pole and a South Pole. Nope. In fact, it breaks up into two separate magnets, each with a North Pole and a South Pole. And if you do it again, it breaks up into two separate magnets again, each with a North Pole and a South Pole. And it keeps on doing that. And in fact, we've never, ever, ever found an isolated North Pole or an isolated South Pole. And we don't believe they exist. We've got really good equations that are consistent with the magnetic monopole not existing. In other words, without a North Pole by itself or a South Pole by itself. One of our equations, which is basically Gauss's law for magnetism, instead of having like Q enclosed over epsilon naught on the right hand side like Gauss's law does, Gauss's law for magnetic fields has a 0, and that's indicative of there being no charges. It would make things a little bit different. The equations would obviously be different, but so far we've never found a magnetic monopole, so we don't think they exist. Now, just like unlike charges attract and like charges repel, well, unlike poles attract, so a North Pole is attracted to a South Pole and a South Pole is attracted to a North Pole, but a North Pole and a North Pole actually repel, and a South Pole and a South Pole repel. So those are some of the basic principles of magnetism and how it works. Like I said, we'll go into much more detail later about how it's caused. But right now I want to talk a little bit about the relationship that actually exists between electricity and magnetism. I will tell you that what Maxwell and Faraday and various other people, Volta and Ampere and Coulomb and all these people were able to put together over basically during the 19th century, which would be the 1800s, was that ultimately the magnetic field and the electric field are two sides of the same coin. And in fact, when relativity comes along, which I've mentioned to you before, special relativity was in fact completely inspired to Einstein by electricity and magnetism. And in fact, electricity and magnetism, as written by Maxwell, is completely consistent with special relativity. It was the equations of Maxwell that Einstein looked at and said, this is the only way I can make sense of the world is if the speed of light is a constant, independent of the motion of the source of the observer. And that's what Maxwell's equations were saying to him. So it turns out when you actually apply, say, a physical problem and apply relativity to it, you can see exactly what I mean by the electric field, the magnetic field being opposite sides of the same coin. So let me tell you that they looked for a long time for some connection between electricity and magnetism, and Ørsted discovered that in fact, when you turned on a current to go through a wire, which remember now we have batteries, thanks to Volta and people like that, we had batteries that could supply a number of charges for a long period of time. So you didn't just get one big flash, coming out of a Leyden jar. So we could actually create these currents going through a wire. And what Ørsted discovered was that if you lay a bunch of compasses around the wire, all the compasses will align in concentric circles. And of course, we know compasses align along magnetic field lines. Ergo, a current carrying wire must create magnetic field lines. And the rule for it is called a right-hand rule. You can put your thumb in the direction of conventional current. So we're assuming positive particles are going this way. And then you look with your right hand, and that's the direction around which magnetic field lines point. So if you look from above, like I'm doing right now, that's counterclockwise to me. So everybody imagine a wire, or use your pencil or whatever, and imagine a current going straight up. Put your thumb of your right hand in the direction of that current, straight up. Wrap your fingers around it and imagine them being like Gumby fingers. Hopefully y'all know who Gumby is. The green clay character from the 70s, I think. So they're Gumby fingers, so they don't have these straight lines. They're just smooth concentric circles. And then if you look down from above, you'll see that they're in counterclockwise circles. That's the direction of magnetic field. So that means on this side, right here next to the current carrying wire, the magnetic field points towards y'all. On this side, it points towards me. In front, it points that way, and behind, it points that way. So that's what I mean. And it's literally, it's tangential to a circle, a concentric circle at each point. And of course, the further you get away from the wire, the weaker the magnetic field gets. So that is what the actual magnetic field caused by a current carrying wire is. And not only that, Oersted was able to show that, in fact, a magnetic field can affect a current in a wire as well. So you might think about it this way. You say, okay, well, what creates a magnetic field? Well, magnetic field is when currents are going this way. And in other words, when positive charges are moving this way, that creates a magnetic field going this way. Well, what if, and thinking about special relativity here, what if we transported ourselves to a reference frame in which the positive particles were sitting still? If the positive particles were sitting still, there would be no current. And if the current is the way we create a magnetic field, then there would be no magnetic field, yet you'd still have to say, okay, well, be that as it may, it turned out that a negative particle or a positive particle going by this way, in fact, got deflected that way, as if it was in a magnetic field. So when you look at it from a relativity standpoint, guess what happens? There's these positive charges that were moving up in the other field. Now that you've moved to the field, to the frame in which the positive particles are sitting still, it turns out that now the distance between the charges has actually shrunk. And in fact, you've got a net charge. Instead of having an equal number of negatives going down per inch and an equal number of positives going the other way per square inch, you now have a plethora of positive charges sitting perfectly still on this side, and a depletion of negative charges going the other way, because you're actually moving at this velocity, and we know that the distance between the charges will shrink. Well, that's enough to account for an electric field. So you do a calculation for the electric field, and lo and behold, you get an electric field that points in the exact same direction that the magnetic field did. So that's what I mean by a magnetic field and an electric field being opposite sides of the same coin. In fact, you can see that the physics would be the same in either reference frame. And that's normally, a problem that you'll do in a junior or senior level physics electrodynamics class. So it's pretty cool to think about magnetism and electricity that way. Now that we have this idea of what a magnetic field is, I want to go ahead and tell you first. I want to draw some pictures of magnetic fields, magnetic field lines, and then I'm going to talk about basically how those magnetic fields affect things. So let me turn on my document cam. Anybody have any questions on that before we split? Okay, I think it's pretty straightforward. It's probably stuff you mostly already knew. Just remember, like poles repel, unlike poles attract. It turns out, in fact, that a magnetic field does apply a force to a current carrying wire. A magnetic field, in fact, applies forces to charges in motion, but if you have a charge sitting perfectly still, a magnetic field does nothing to it. Okay, so let me turn on my document cam. Okay, so looks like my cat's been in here. Got all my stuff fixed up right, real nice, don't she? Turd ball. Such a weirdo. This way. There we go. Okay, so that looks pretty decent. Okay. So first off, as we were talking about the magnetic fields, a typical magnet might be a bar magnet. And of course, there's different shapes. You've probably seen horseshoe magnets and bar magnets. There's obviously other types as well. But you might say this is the north pole of the magnet and this is the south pole of the magnet. And what I was saying is that the magnetic field lines, in fact, leave the north. So they exit the north and enter the south. So they look sort of like this. It should be fairly symmetric. And you see they're entering the south, and then they continue along a straight line inside of there. There'd be a symmetric one right here that, if properly drawn, will look exactly the same way, a mirror image, in fact. And that means this points this way and this points that way. So that's a typical electric field line. In fact, there's more in here. You can have another one over here. Notice how much closer they are together. So the strength of the magnetic field is quite high near the poles of the magnet, and then gets quite weak out here, because all of these, of course, loops have to continue and come back and hit another part of a loop, or else it's not a real magnetic field line. because all magnetic field lines complete circles. And in fact, whenever we see a natural phenomena that appears to show up in loops, we think of either certain types of flow of like a gas or a liquid, or we think of magnetism. So for instance, a lot of the loops we see at the surface of the sun, that makes us think magnetism. And sure enough, we later saw a very specific signature of magnetism in the spectra of stars, and that allowed us to figure out basically what a big part of what was going on in the sun. So that's what the magnetic fields look like. With a bar magnet, of course, with a horseshoe magnet, of course, you'd have something like this, and one side would be north and the other side would be south. And obviously, what you're looking at would be lines of magnetism going like this. And then because of the lack of symmetry, it does some crazy stuff, maybe like that. And maybe even like that. We also can put, if you take a really big north pole of a magnet and put it really, really close to a really big south pole of another magnet, then you get a fairly uniform magnetic field going straight through here. It looks like the lines end, and that's just because we have to, because it's got to be such a big drawing, but they'll start to stretch out a little bit left and right as you get closer and closer to the edge. So that's basically how the magnetic fields look. And there, of course, all these things are in 3 dimensions. So if you imagine rotating this diagram through 3 dimensions, you sort of get you get something that look like the stator in say a alternator of a car. So in other words, loops and then loops and then loops and then loops and then loops like that. So a lot of different shapes going around, almost like a donut, if you will. All right, so now what about forces? Does the magnetic field cause any force? And it turns out it does. In fact, it turns out the force due to magnetism, which I'll subscript B just to remind you that it's magnetism. B is a symbol we use for magnetic field, by the way. Some books use H and stuff like that. And some books use entirely different units, but they're actually doing entirely different things than what we're calling a magnetic field. So just bear with me. And when you get to another course, for instance, if you become a double E major, then you might actually use units other than the Tesla or the Gauss for magnetic fields. You might use Webers per square meter or something like that, which actually is the same one, but either way. So here's the force. It happens to be proportional, say, to the current going through the wire. So we're imagining a current carrying wire. So here's our current carrying wire like this. And let's say there's a current going that way. It turns out the force on this wire due to a magnetic field that actually exists is actually proportional to the strength of the magnetic field. It's proportional to the current going through the wire, and it's proportional to the length of the wire that's actually submerged in the magnetic field. But it also turns out that it's a weird force in that this force is not parallel to B, it's not parallel to I, but rather mutually perpendicular to both of them. So that if you had the magnetic field, let's say going like this, at some angle, say theta, okay, that's as if I is a vector, the current is a vector, and B is a vector and they're tail to tail, then it turns out it's also parallel to sine of theta, or excuse me, proportional to the sine of theta. So we can ultimately write this by recognizing this sine theta and the ILB, and the direction, by the way, is, get this, we put our index finger, our fingers of our right hand, say, in the direction of the current carrying wire, in the direction that the current's going. So that allows my hand to be in any of these positions, because all of those positions are still parallel to the current, right? But then I have to orient my hand so that my right hand fingers can curl through the small angle towards B, right? In other words, this would be the big angle and this would be the small angle. So I have to curl it that way. So you now see that my hand has to be like this in order for my fingers to curl towards B. And then if I extend my thumb of my right hand, I see that my thumb points in the direction of the force. So in this case, the force would actually be into the page. And the way we mark into the page is we put a circle with an X in it. To me, I like to tell students it's like this. If you're looking at the end of an arrow, you basically got those little feathers. Right, and here's the arrow, and then the tip of the arrow is like that. So if you look at this end, it looks like that. If you look at this end, it looks like that. So that's what we're doing. We're saying the magnetic field is into that. Now that you got that, you probably can recognize that the force due to the magnetic field on the current carrying wire is in fact F is equal to I L. Let's treat L as a vector that happens to be the length of the wire. And it's not the whole length of the wire, it's just the length of the wire that's submerged in the magnetic field. But if you assume L is the wire straight and L is exactly the length of the magnetic field of the wire in the magnetic field and goes in the direction of conventional current, then you can treat it like a vector and you'd say IL cross B and you'd get the exact formula. So that turns out to be the right equation. So in this case, let's say L, so here's example 1. Let's say L is equal to 12.0 centimeters. Let's say I is equal to 20.0 amps. That's a big amperage now, okay? Like 10 gauge wire for that. I think 10, you might be able to do it with something a little small like 12, but I think it's 10. Anyways, and let's say the magnetic field B, and I haven't introduced you to the units yet, but the unit for the magnetic field that we generally use in the SI is called the Tesla, named after Nikola Tesla, who I think we decided was Serbian. I think you can tell the Tesla is equivalent to 1 Newton per amp meter, and that's actually correct. So let's say this is going to be in a 0.0100 Tesla field. Turns out the Tesla is a big unit. To give you some idea, our Earth has a magnetic field equal to 0.5 times 10 to the negative 4th Tesla. So that's how, you know, the Earth is basically half of a 10,000th of a Tesla. But in this case, in this diagram right here, we see, let's say theta is going to be equal to 60 degrees. And then I can say, okay, well, F is equal to I times L times B times the sine of theta. That is going to be 20.0 amps times 0.120 meters times 0.0100 Tesla and times the sine of 60. Well, if you remember your 30, 60, 90 triangle, 60 is here, and the opposite of 60 would be root 3. Opposite of 30 would be 1, that'd be 2. So sine of 60 is root 3 over 2, or about 0.866. And of course, I don't have my calculator here. That would be awesome if I had that. Oh, I found another one. Hopefully this will work. Oh, good. It's not. I thought the battery was dead. That's scary. Okay, so let's do this. So 20 times 0.12 times 0.01 times, and I'm going to say the trig function sine of 60. And it looks like I'm in degree mode with this calculator I just randomly found. Oh, great. Now I got to remember how to convert this to a number because I'm using a calculator that I'm not used to. So 0.0208. Newtons. Okay. Because a Tesla, like I said, is a Newton per amp meter. So when you multiply a Tesla times an amp meter, you're just left with a Newton. So 0.0208 newtons, a very small force, in other words. And of course, that's not that small of a magnetic field, that's actually, you know, on the order of 1,000 times stronger than the Earth's magnetic field. In fact, there's another unit of the magnetic field. The magnetic field B is also equal to a Tesla. That's the one we told you already, which is just abbreviated capital T, but it's also given in Gauss, which is 10 to the -4th Tesla. And your book even mentions that that's equivalent to Webers per square meter and stuff of that sort. Let me double check what I just don't want to leave out any ones that it did say it was equivalent to. I think that was all. They just talked about the Weber per square meter. I don't even see it now. Completely disappeared. Maybe I'm on the wrong page. Yes, there's peers that I might be on the wrong page. Ah, yes. So yeah, Weber per square meter is also a Tesla. And we'll learn what a Weber is a little later, but surprisingly, it has nothing to do with a gas grill. Yeah, that's my dad joke for the day. All right. Anybody have any questions on that rather straightforward equation? All right, so let me show you something else. As long as we have a nice straight chunk of wire whose length we know within the magnetic field, then this F equals I L cross B is great, and that's what I want you guys to use, so you can get the direction and everything, and you can start thinking more geometrically. But what if, for instance, the wire actually curves, and what if the magnetic field is not uniform? Well, that brings us to example 2. I'm trying to do something a little bit more complicated than the one your book does, but not so complicated that you won't understand that easily. So what I'm going to do is I'm going to draw a coordinate system like so. So this will be my x-axis, and this will be my y-axis. And what I'm going to do is I'm going to have a current carrying wire coming in from the right, like so. The current is going that way. It's going to carry a current I. It's going to get to a radius big R and go half a circle. So that's R there too, even though it doesn't look like it. Okay. And then it's going to come towards the origin and go to a radius little r, and then hang a right and leave this way, again arriving at r. So let me make sure you understand that that's clearly along the negative x-axis. So everybody see that shape? What I'd like to do is calculate the force, or excuse me, the total force on this particular wire, assuming it is submerged in a electric field. So I got to figure a relationship for my electric field. And I'm going to say the electric field is into the page. So let me use my little green pen to show the electric field's directions. I'm going to say it's a uniform electric field. So you see that the electric field is basically uniform everywhere, and it goes into the page. Now what I'm going to do is render this L cross B in a differential form, and I'm going to say that dF is equal to I dL cross B. like that. So I can break this down into several parts. I'm going to call this part 1, this part 2, this part 3, this part 4, and this part 5. Okay, in other words, the straight part is 1, the curve is 2, the 3 is a straight part, the curve is 4. So obviously the odds are all straight parts and the evens are all curved parts. Okay. So first off, if I look at df sub 1, I get I. Now in this case, the dl is just going to be negative dx I hat. In other words, I'm choosing to use my differential as the indicator of direction, and I will just use a positive small coordinate to a large coordinate for the range of integration. And then I'm going to cross that with B, which I'm going to say B is a uniform magnetic field. Since it's going into the page, we see X, Y, Z would point out. So B is ought to be actually some constant B0 times the negative in the K hat direction. The negative makes it go into the page. Okay. So the dx is in the I direction. The B is in the negative B0 K hat direction, like that. And what I see here is I'm going to have a magnetic field IDX cross B. And when you cross product I hat cross K hat, that's I hat cross K hat, you get a force that acts downward. Okay. So that force would actually just act downward. So the integral, let's see, F1 is equal to the integral of dF1. And we're going to get a positive. Notice the I and the B0 are constants. That's positive I, B0. I just did a cool trick with a cross product by cross producting the vector portion, I cross K, okay? I cross K actually is in the up direction. I was doing it with the negative K earlier, but I cross K is in the up direction by my right hand rule. So I know the actual direction is going to be in the Y direction. So I can put a Y hat after it, or excuse me, a J hat after it. And then I just get dx from x equals, I'm going to just stay it started right here at 2r. So we'll say from x equals r to 2r. Remember, I chose my direction with this, so I'm just going to call r to 2r the coordinate. So this one actually gives me a 2r minus r times ib. So that'd just be r I b in the j hat direction. So that's my force due to that little piece of wire. You'll see later that when we do like try to calculate the magnetic field here at the origin, we'll see that these little parts won't matter because they're actually parallel to the R. Now I'm going to do part 2. So dF2 is going to be, what I'm going to do right here is I'm going to say that is an angle theta. Notice it's measured counterclockwise from the x-axis. And in fact, this is in what we call the theta hat direction. So I'll say I. Now, in this case, the DL would be R d theta, theta hat. Okay, theta hat is just a unit vector that points in the direction of increasing theta. Notice it's just perpendicular to a radial line, so I can work that out, and I'm going to work that out in terms of i's and j's, because when you integrate with i's and j's, you don't have to do any calculus on the I and j because they're truly constants. So in this case, I'm going to say the dl is r d theta, and then that's pointing in the theta hat direction, and that's got a cross product with basically the negative B0 K hat. Okay, now theta hat cross k hat gives me basically a negative r hat. So I can work this out and say I negative b0 r integral d theta in the negative r hat direction, because again, this is my theta hat. It's perpendicular to that line, right? I got to curl my roll my hand over until I can curl my fingers into the page, and then this is going to now be pointing parallel to that, and that is the r hat direction. So that's the negative r hat direction. So I will go off here on the sidebar and realize that this right here, if this is the angle theta, then this r hat would be cosine theta I hat plus sine theta j hat. And then, of course, if I go 90 degrees to that, this would be theta hat. And of course, this is theta. So this would also be theta right here. So you can see that r hat is equal to cosine theta I hat plus sine theta j hat. Just so you'll know. So now we can, figure out what this is about. Now we get from here, you can see that the x component is going to be negative sine. So theta hat would be negative sine theta I hat, and cosine of theta would be the y component. So it'll be plus cosine theta j hat. You can see that if you take the derivative of this with respect to theta, you get theta hat. So that's what those really are. That's what that theta hat is. That's what that r hat is right there. And whenever you have to integrate something like that, you have to break it down into that. So now what we're going to do is we're going to say, okay, well, F2 is equal to, let's say, negative RIB times the integral of cosine theta I hat. Was that negative from this, or was that negative? Oh, got another negative. So that's actually positive now. I had the negative there and that negative there, so that made it positive. Cosine theta I hat plus sine theta j hat d theta. Again, I wrote this I hat and theta hat in here because they have to be in there, but they're constants, so you really don't have to integrate them. So I'm going to take the integral of cosine theta from theta equals 0 to, of course, pi over 2. And I'm going to do the same thing with the sine theta. So in this case, I get RIB theta. Now, cosine of pi over 2, let's look at our trig functions just to refresh ourselves. Cosine looks like that. This is pi, and therefore that's pi over 2. So I'm going to get cosine of pi over 2, which is 0, minus cosine of 0, which is 1. So I'll get 0 minus 1 I hat plus, now our sine theta is like that, where that's pi. And of course, that's pi over 2. So pi over 2 would be 1, and 0 would be 0. So this would be pi. Oh, wait a second. I got to integrate it first. Almost forgot that. The integral of cosine, of course, derivative of sine is cosine. So the integral of cosine is sine. So this would be sine theta I hat from 0 to pi over 2 plus, I'll put a curly bracket out there, plus the integral of the derivative of cosine is negative sine. So the integral of sine is negative cosine. So that's negative cosine theta 0 to pi over 2 j hat, and then my curly bracket. So now I can say, all right, well, the sine of pi over 2, that was the 1, and the sine of 0 is 0, so that'd be 1 minus 0. Okay, and then the negative cosine of pi over 2. Cosine of pi over 2, of course, is 0. And then cosine of 0 is 1. So it's going to be 0, negative of 0 minus 1 j hat. So you can see the negative of that becomes positive. So it'll be just RIB times I hat plus j hat. And what that really means is, in fact, this force should actually be perpendicular, or excuse me, I should say a 45-degree angle right along here, because it's, notice it has the same magnitude of the I hat and j hat component. So the magnetic field, if you just imagine part of this being a positive particle, that positive particle, let's say right here, is going this way. So the force is actually going to pull it that way. I must have dropped a negative somewhere. Where did my negative go? Let's double check that. So I got RD theta. That one's the right direction. That one's the right direction. Theta hat cross K hat. Theta hat cross K hat is negative R hat. So that was there. Oh, okay. Yeah, I doubled up. Sorry about that. So yeah, this ultimately should have been a negative. Notice what I did is when I took the cross product, I actually took negative K hat. So that negative should not have been there. And then that would have made this whole thing negative. So that makes more sense. So I'll get rid of that negative right there. Everybody see that? And then we will leave the negative in here. So get rid of this plus sign. Call that negative. Call that negative. Call that negative. So I'll see F2 is equal to negative RIB 0 I hat plus j hat. And that just means, like I said, it's pointing directly this way at a 45-degree angle, just due to that part. So now I've got a force that obviously from the first part was pointing in the j hat, the positive direction. I've got this pointing this way. Now I've got to do this one as well. And that's obviously has a length r minus r. But it is in a uniform magnetic field, so I can do that a lot easier. I don't have to actually do this. I didn't have to do it then either, because it was, basically supposed to be in a uniform magnetic field. So I should have just got I times L, 2r minus r is r, times B, which is exactly what I got. So I can do that same thing with number 3. So F3 is going to be, the formula should be r minus little r times I times B0. Now the direction is, notice the current's this way and the magnetic field's that way. So it should point in the positive X direction. So I'm going to call that I hat. So that's another force. Now I can do this way. And let's imagine this angle right here is theta, and I'll say dF4 is equal to, and notice this is in that same theta hat direction again. So dF4 is going to be I times little r d theta. That points in the theta hat direction. And that's going to be cross product with negative B0 K hat, which is easy enough. I'll pull out this negative out in front and I'll say negative RIB0, and then theta hat cross K hat, because I got the negative out in front already. Theta hat cross K hat gives me, again, negative R hat. So this one's also going to be in the negative R hat direction, times d theta. So F4, I can do just like I did before. F4 is going to be the integral of d4, dF4, which is going to be negative and negative. This time it's going to come out positive. Hopefully we get a negative from our range of integration, because it's got to point inward. We just know that from the physics of the problem. It's got to point radially inward, which is, same argument I made there and found that minus error because of it. So I'll say negative R I B0 times the integral. Now I've got a R hat wait a second, this is negative and negative. Yeah, that's positive. So I got to have a range of integration. Hopefully it gives me a negative, like I was saying. So r hat we found was cosine theta I hat plus sine theta j hat, all that integrated over d hat, d theta. And this time we're going to integrate again from 0. I guess I don't have to actually do that. Let's see. If I'm using theta hat, I sort of have to. Oh yeah, this should work. I'm going to go from 0 to pi over 2 again. I think this should work, but it looks like I'm going to get the same stupid signs. Integral of cosine is going to be sine, and then the sine of pi over 2 is just going to be 1. That should be positive. It's definitely going this way, so that's IDL. I'm looking again because it looks like I'm getting ready to get a positive when I know this should be pointing radially inward. I'm wondering if I have to actually, I don't know why I would have to, because I just defined theta to start right there. Why should I be beholden to that being theta equals, pi over 2 to theta equals pi? Let's do that. Oh yeah, I guess I have to because I'm using the theta hat. So the theta hat has a very definite definition. So yeah, instead of going from 0 to theta over, or to pi over 2, I'm going to go from pi over 2 to pi, because I've used a construct that's based on the units. If I was really treating this as theta equals 0, then I'd have a different function for what theta hat and r hat were. So that's why I have to actually use the original definitions of theta, where this theta is pi over 2 and this theta is pi. So yeah, I think that makes sense. All right. So now I'm still going to get the same integral. It's going to be equals plus RIB0 times sine theta from pi, 2 pi from pi over 2 I hat plus negative cosine theta from pi over 2 to pi j hat, with that bracket like that. So the sine of pi obviously is 0, which we can see there. And then the sine of pi over 2, of course, is 1. So this is 0 minus 1. And then the cosine of pi over 2, we can see is 0. And then the cosine of pi is negative 1. So this is negative of negative 1 minus 1. Wait a second. Cosine of pi over 2 was 0. That's what. Sorry about that. The positive 1. Okay, so the y component is going to be positive. That makes no sense. So the integral of sine is in fact negative cosine, because the derivative of cosine is negative sine. That part's right. I did go from pi over 2 to pi. Cosine of pi is equal to negative 1 minus cosine of pi over 2 is 0. So it's negative 1 minus 0, negative would be plus. So for some reason, in this case, I'm getting RIB0 times negative I hat, which that's consistent. We're supposed to be going that way, but it shouldn't be pointing up that way, because then the force is this way. That doesn't make any sense. So I know somewhere along here there's an error of a not minus sign in here, but I will tell you right now, write this as minus j hat, and I'll put a square bracket around it, and that's the actual F4. So I'll box this off with a different color and say that's correct, but I didn't get it. Somehow I made a mistake in getting it, because I ended up coming up with a positive, but I know for a fact it's got to point this way, which would have a negative a negative X component and a negative Y component. So somewhere along the lines, I dropped a negative, but either way, I've got that. F1, I didn't label that. F1 was like this. And then finally, F5, that's another easy one. So F5 is a straight line. Again, let's say this goes out to 2R. So the length will just be 2R minus R, which is R. So F5 should just be R times I times B0. Of course, IDL is this way. K hat, the magnetic field's pointing down. So this will actually be in the negative J hat direction. Actually, it should be in a positive J hat direction, right? IDL cross V, just like that one should have been in the negative K hat direction. Oh yeah, that was supposed to be a negative 2. All right, so that's it. Again, I tried to make one a little more complicated than the one your book does. Your book just did one that basically had a current going up, a half circle, and then a current going down, which I think is a little too simple to let you lift off from there and do other things. Just because the force on this side cancels out with the force on this side, I want to show you that it doesn't always have to be that way. This one and this one can add up with this one and this one, and you get a total net force of the sum of all these things. So the total force on this, of course, would be adding all these up. Again, somewhere along the line, I made a sign error because I know I should have had a negative and a negative there, but somewhere mine came up to be a positive. So keep an eye on that. I don't know where it came from, but there's obviously something. I did have an R hat, right? That was what it was supposed to have, was an R hat there. Yeah, it looks like an R hat and a negative, that became positive. This was negative before. So yeah, all that looks right. Anyways, anybody have any questions on that nasty, ugly problem? All right, well, we'll go on from there. So that's sort of the nastiest type of problem you would do here. In the next chapter, we'll do something called the law of Biot-Savart, and that is like that, only worse. Meaning it's going to have a cross product in the integral. Yeah, it's just really nightmare. But the good news is, just like we had that horribly tough Coulomb's law in integral form, then we found Gauss's law. We're going to have a really tough Biot-Savart law that I just told you about. And then we're going to have a simpler version called Ampere's law that, you know, as long as the symmetries are pretty high, you can apply to solving for the magnetic field. So that's going to save us. Now, in addition to that force, it turns out that the reason, or one way of thinking about the reason why a current carrying wire experiences a force is because the individual charges, when they're in motion, experience a force. And in fact, that force is given by F equals the charge of the particle times the velocity of the particle crossed with the magnetic field. So QV cross B. Okay. So remember, our cross product actually means a determinant. I'm going to go ahead and do an example like that. So let's imagine, for instance, an X, Y, Z coordinate system. So I'm going to say this is X, this is Y, and let's say this is Z. And let's imagine an electron traveling in this direction, and V of the electron would be, let's say 3.00 times 10 to the 5th meters per second in the negative I hat direction. So in other words, it's going in the negative X direction, right? And let's say our magnetic field is uniform. Let's say B is actually equal to 2.00 Tesla. And let's say, in fact, it's pointing in the K hat direction. So out of the page. So remember what happens when you multiply a vector by a scalar. if the number's bigger than 1, it makes it longer. If the number's smaller than 1, it makes it shorter. If the number's positive, it doesn't change the direction at all. But if the number's negative, it flips the direction. And in fact, in this case, we've got Q is equal to negative 1.602 times 10 to the negative 19th coulombs. So that's a negative. So even though V is this way, QV is this way. So I have to orient my hand like this, and actually I can do it all these different ways like that. Those are all fair game until I realize that the magnetic field is actually pointing out of the page. So the magnetic field pointing out of the page, now I have to go like this, 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 and then I realize, okay, well, I've got to be able to turn my fingers towards the magnetic field, which other than the drawing, notice the drawing, I'm pretending like out of the page is this way, but in reality, out of the page is straight up towards the camera. So I put my hand like that, and now I can curl my fingers towards B. And in fact, my hand points, my right thumb points in the negative Y direction. So that's the way it should be. So let's go ahead and do this brute force with a cross product. So first off, I'm going to say 3e to the 5th times 1.602 e to the negative 19th. This is why I do not like this calculator. There's a way you're supposed to be able to change the mode, but I can't remember it to save my life. I just have to do this afterwards. Give me a friggin' fraction. 4.80. I'm going to call that 4.81. So QV is 4.81 times 10 to the negative 14th. And that turns out to be coulomb meters per second. Not to be confused with centimeters per second. Okay, so that's QV, and it points, of course, in the negative I hat direction. Excuse me, it points in the positive I hat direction because it was already in the negative I hat. And then I multiply it by negative and get it positive. Okay, so now I'm going to do just nasty brute force cross product calculation using the matrix, just to remind you in case you guys are rusty. So QV cross B means I'm going to take and calculate a determinant of a matrix, the top column or the top row of which is I hat, J hat, K hat. The second row of which is QV, which obviously I'll just say 4.81 ... Okay. And that has no Y component or K component. And then, of course, the magnetic field has no X component or Y component, but does have a 2.00 Tesla K component or Z component. Okay. So the way you're supposed to do this is you say, okay, well, this is the 1, 1 spot, and you go -1 raised to the 1 plus 1 power is -1 to the 2, which equals 1, because the -1 is in parentheses. So that means -1 times -1, which gives you a positive. So I now cover up that column and that row, and then do the determinant of this. Well, the determinant of this is 0 times 2 minus 0 times 0. So I get 0 I hat. Now this one is row 1, column 2. So this is -1 to the 1 plus 2, which is -1. So the way I compensate for that, you can do it a lot of ways. You can just put a negative in front of it and do the regular stuff. What I do is I do the determinant backwards. So I'm going to say plus, and now I have to cover up that column and that row, and then I do the backwards determinant. The backwards determinant would be 0 times 0 minus 4.81 times 2. So that's going to be 9.62 times 10 to the negative 14. And that result should come out in Tesla coulomb meters per second. That was 4 times this, so it would have been 0 minus this, so I actually have a negative in front of that, and that's going to be my j hat component. And then finally I do this one, and this one of course is -1 to the 1 plus 3, which is -1 to the 4, which is 1. So this one I just do a regular determinant, but I cover up this row and this column. That'd be 4.81 times 0 minus 0 times 0, so that's just 0k. So ultimately I get that F is equal to Q V cross B, which we found was -9.62 times 10 to the -14th. Now remember, a Tesla is a Newton amp per, or excuse me, a Newton per amp meter. So I'm going to write Newton per amp meter in place of the Tesla. And now I'm going to write the Coulomb times meter per second. Notice a Coulomb per second is an amp. So that amp cancels out with that amp, that meter cancels out with that meter, and I've got, don't forget my j hat, -9.62 times 10 to the -14th newtons j hat, and we did expect it to point in the negative y direction from our right hand rule, so that gives us a good check. Any questions on that? Okay, well, the nature of this force, and by the way, I was making my schedule for next semester, and I discovered that lo and behold, your class is supposed to be over at 6:05, and I've been consistently keeping you till 6:10 because I was thinking it was over at 6:10. So I apologize for that. That was example 3. Let me double check that. That was example 1, 2, yeah, example 3. Let's do example 4. So this example is going to help us understand aurora borealis and stuff like that. So it turns out that if you take, say, a positive particle and it's moving in this way, and then let's say a magnetic field points into the page. So it enters a magnetic field area. What's going to happen as soon as it gets in there, which let's say is right here, QV, since it's a positive particle, QV is that way. I turn my hand like that so my fingers can curl towards B. That means the force is in the upward direction. So it's going to feel a little bit of a force this way. Well, then it's going to, of course, turn and start going this way. So then QV points like that. And that means it points this way. But notice it's always perpendicular. So it's F this way. And if this magnetic field, it covers a big enough area, then what's going to happen is it's going to tend to go in a circle. And if there's no component of the velocity parallel to the magnetic field, then it'll just stay in that flat circle, which I think you guys recognized from your last lab. Y'all recently did magnetic deflections, right? So that was actually electrons moving through a magnetic field that was pointing through the center of some loops called Helmholtz coils. And what you have is this will actually make a circle. So using the summation of forces equals mass times acceleration, we can say, oh, well, QVB is equal to mv squared over r. And that's just using our centripetal acceleration formula. Notice this v squared cancels out, leaving a v. And I can say that, for instance, the r, the radius of curvature, is just going to be mv over QB. So that's a derivation of the circle of radius, the radius of the circle, that a proton or whatever kind of particle of mass m and charge q will experience in a magnetic field B, assuming the initial velocity is perpendicular to the magnetic field. Okay. Now, as you notice, when something completes a circle, of radius r, it's gone a distance of 2 pi r. And that time required for something to complete a circle is called the period. So that v is actually equal to 2 pi r over t. So with that, you can actually say, okay, well, t, the period of the actual thing, should be 2 pi r over t, or excuse me, over v. But you can also plug in your v now. So let's say v is equal to qbr over m. So I'll say 2 pi r over qbr over m, which means the m will come up on top, and I'll get t is equal to 2 pi m over qb. Because notice the r's cancel out. So in particle accelerators, that's exactly what we do, is we need to know things like the period, the frequency. Of course, frequency is 1 over the period, so that's qb over 2 pi m. So that's another expression. So those are all some commonly used expressions. Now, if this particle, instead of just going purely to the right, let's say it had a little bit of a component this way. Well, that component would feel no force whatsoever. So what the particle would do is it would make a circle, but as it's making the circle, it's going this way too. So it's going like this. Anybody know what shape that would be?
Ellipse?
Well, it's still going to stay in a circle, but a circle that sort of spun up like this. Can you think of an object shaped like that?
A spiral.
A spiral, yes. Our helix is basically the shape of a spring. So if v, let's say v dot b, remember the dot product pulls off components that are parallel. If v dot b does not equal 0, then the path is a helix, not unlike your DNA. It's a helical path. Helical. And that's what happens at our north and south pole. The Earth is sitting like this. It's got a south pole of a magnet up here. It's got a north pole of a magnet down here. There's the equator. There's the North Pole. There's the South Pole. And basically what it's got is these magnetic field lines that come like this and go like that. Well, the Earth puts out something called the solar wind, which is a bunch of little positive and negative particles coming flying in this way. Well, they get near a field line and they definitely have a component parallel, but they also have a component perpendicular. So they spiral around like this and hit the upper atmosphere. And when they do that, they actually cause the molecules and atoms in the upper atmosphere to become ionized, meaning they like knock electrons loose. Well, then the electrons fall back into their places, and when they do, they emit light, and that light is a characteristic color that has a characteristic wavelength associated with the energy between one level and another. So you get these really pretty colors. When it happens up here, it's called aurora borealis. And that's just because the Latin word for boreal, for north, means boreal. And you're going to be surprised by this one if you didn't already know it. Down here, it's called the aurora. Aurora just means light, by the way, or color or something like that. Aurora australis. So yes, Australia comes from the Latin word for south. And of course, anybody want to guess what orientalis means? Anybody know what that means? Have you ever heard of anything that sounds like Orient or anything like that? It's a more or less an unacceptable phrase for people from Eastern Asia. oriental, and orientalis means east. I think it's Occident or Occidentalis, something like that, means west. But anyways, Oxendine, Maryland, I think, is a town, but that's named after the west direction. So that's what causes the aurora borealis. We now know that. Now, one more thing or two more things I want to cover. There is existence of something called a magnetic dipole, just like we studied in chapter, I think it was, well, we started in 21, but we did it other places as well. I should point out that in addition to a force due to a magnetic field, we also have the original force due to the electric field, so that the net force is called the Lorentz force, and that's Q times E plus Q times V cross B, which can be written as Q times E plus V cross B, and that's called the Lorentz force. So you can do neat things with that. For instance, you can figure out whether positive particles or negative particles are the current carriers. That's called the Hall effect that I warned you about some time ago. And in fact, if you connect a circuit in such a way that it's inside of a magnetic field, let's say we have a magnetic field that points into the page. Now, if they're positive charge carriers, let's say the charge carriers are positives. So let's draw them red, say. If it's a positive charge carrier going this way, meaning this is high voltage and low voltage, okay, then what will happen due to this magnetic field is QV cross B will actually cause these guys to follow along there, and you'll get a bunch of positive charges up here and a bunch of negative charges down here. So if this voltage at this height then you'll know positive particles are the charge carriers, are the current carriers. However, if you did it with a negative charge carrier, then that would mean the negative charges are in fact going this way. Well, a negative charge would still have QV going that way, only that would force this side to have negative charges and positive charges to be over here. And in fact, this side would be lower voltage, and this side would be a higher voltage. It turns out experimentally, this is really what happens. So that's called the Hall effect. Hall effect. You can also see that, for instance, if you had voltage, an electric field, and a current, and a magnetic field acting, you can actually use that to be a velocity selector. So you let little particles come in here, and if you set up the velocity such that the velocity is actually E over B, then only those velocities will come through, because what happens otherwise is you've got a QVB is a force causing it to say go up, and you got a QE is the force causing it to go down. If those two do not equal each other, then the particle is not going to be able to make it through the next slit. So that's like a velocity selector. And you can use it also for a mass selector using the radius of curvature, stuff like that. Now, the last part is the electric dipole that I want to talk to you about. I'll let you read the mass selector, mass spectrometer. I'll let you read that on your own. It's pretty straightforward. But what I want to talk to you about is something called electric dipole. And it turns out that basically, if you want to think on the microscopic level, what actually might be causing magnetic fields, you can sort of think that somewhere there exists some kind of current going in a circle. So if you imagine, for instance, a magnetic field, pointing this way. So you see the magnetic field pointing to the left. I know that green's hard to see, but I'm trying to show different colors. So let's imagine now that we got a wire, and let's say we've got a wire connected to a little spindle that goes around like this, comes back like this, and then of course this is a little spindle that's free to spin like on an axle or something. So this thing can rotate. And let's say that in fact the current is coming in this way, and the magnetic field of course is going that way. What you see is there's no force here, so, and there's no force here because the magnetic field and the current are in the same direction, right? However, here you've got QV going that way and you got B going that way. So in this case, the force actually points out. And over here, let's call this dimension, by the way, let's call this B, and let's call this dimension A. Over here, you've got a current going down. So QV is this way. That means it's going to go into the page. So that's Fn. And in fact, since the wires are the same length, the magnetic field and everything the same length, those two forces are the same. Okay. Again, F is equal to 0 up here as well, though. So what you'd say is there's going to be a torque on this that's tending to rotate this way. And that torque would be the force F equals Bill, F equals B times I times L. Well, L in this case is A, so that's B times I times A. But torque is force times lever arm, and the lever arm is 1/2 B. The other side has the exact same thing, which is BIA, and this is excuse me, BI, dang it, it's BIA, and then lowercase b over 2. I don't know why I wrote just plain 2. Lowercase b over 2, because b over 2 is the lever arm. Y'all see the lever arm just goes from here to here. That's b over 2. So because of that, I get B times I times really what it amounts to an area. A times B is the area of this. And in fact, it turns out that we can define the magnetic moment, dipole moment, as N, the number of turns, times I. In this case, there was just one turn, but you can't have any number, times the area. And we just defined a vector A as the area given by the right-hand rule, meaning if the current goes around this way, you take your right hand and that's the direction of A. So that's another right-hand rule. And then you find that the torque on a current carrying loop is Ni times A cross B, excuse me, Ni times A cross B, which is of course mu cross B, which is exactly the same result we got for the electric dipole. And in fact, if you go through the same process, it turns out the potential energy can also be written as negative mu dot B, which is the same thing we got for the electric dipole. So that's it. That was the last part I wanted to show you guys. We're now done with chapter 27. Feel free to stick around and ask me any questions you might have. Of course, everybody's free to go. I kept you 2 minutes late this time. Sorry about that. And I have to make this up to you. I might have to start ending class by 6 for a couple days to make up for all the times I kept you till 6:10. But yeah, very good, Gavin. Sorry, I didn't catch that earlier. Anybody have any questions? Otherwise, you're free to go. Don't forget to get your test done.
Thank you, Professor. Have a good night.
You're welcome. Thank you all for coming.
So is the test due Wednesday or Sunday?
There's something due March 1st. That's test 3, I believe, and I think the test 2 might have already been done. Already been due. Let me check.
Yeah, I think it was already due.
Yeah, that's what I was thinking as well. And March 1st isn't till what, Sunday? I think that's Sunday. Well, I don't know.
I think it's
Yeah, test 1. February 14th is test 2. So yeah, that was already due, but test 3 is March 1, which if I look at my Windows calendar, that is a week from today. No, it's a week from tomorrow.
Okay, and then so the midterm will be is that the day after that?
It's going to be, I just was looking at that. Let me see if I still have that document open. It's the Thursday before we go to spring break. I know that. And yes, of course I closed that document. So I think what I want to say is I want to say that spring break is not this next week, but the week after.
Yeah,
So I think it might be like the 3rd.
okay.
Okay.
Okay, and then yeah, so and for the midterm, is it like the same setup as how our online tests have been?
No,
I mean,
this one's it'll be a respondus test where you have to have your video camera on you. You've got to go through some steps showing your work area, showing your blank paper, give a picture ID next to your face so we can tell it's you, and all that stuff. You'll be given a lot more time, but you're not allowed anything but an equation sheet, and specifically the equation sheet that I put up at the helpful documents page, which is the printouts of those from the book.
Okay. And so as for like the questions, are they like the same type of questions that are on
I guarantee that 80% of the points on the midterm will come from questions you've had in the past practice tests. So at least 80% of them will be, and sometimes it's literally a whole 100%.
Okay. All right. That was all I had.
All right. See you, Sean.
Right. Yep,
James, do you have a question? All right. Looks like James might not be here. No question, James? All right. Talk to you later, everybody.